Okay, guys, let's see here. So there's been some questions about grading and midterms. Let me get some issues on the table. The first is I need to check MMS. This is for me, not you. I need to check MMS to make sure that the weighting is set up correctly, because there's some question about that. The second thing is that there's a question about the midterm and how does that work out. For each semester, the midterm is worth 20%. And then each quarter is worth 40. Like that to get 100% of the semester grade. Well, in the second semester, you have no exam, so how does that work out? Well, the easiest way to think about it like that would be ignoring the percentages for a second and just treating these as weights, is that you have a total weighting of 180% or 180, and the midterm is 20 of that, so your midterm is worth 1/9. Which is going to be 11 to 20% of your final grade. So let's just run some quick numbers here. Kenneth was nervous about how this might all work out. First of all, just to let you know, people usually do well in midterms, but there's that. But the second thing is, let's say you're really nervous, and let's say that you've got, I don't know, 94 average cruising into the midterm, and all of a sudden, let's say that you throw up on the answer sheet and you end up with a 20% on your exam. That's unrealistic. Nobody's ever got 20% on the midterm exam. But let's just say that happened, because we like to imagine worst case scenarios. So if we take, looking just at the semester 1 grade right here, if we take 80% of 94, and we add that to 20%,
that's first one is 75.
And then the second one we add another 4.
Yeah.
79. Right. Is a 79.2. So in the absolute horrible worst case scenario, you still end up with something that's pretty close to a B. I would certainly give you a B for that. All right, let's bump that up and change our scenario a little bit so that it's more realistic. Let's say that you had a bad day and you ended up with a 70%. Well, let's keep that down and do a second analysis right here. We don't need to even crunch the numbers to see this. Just adjust this average by doing 20% of 50, and 20%, which is the difference here, and 20% of 50 would be 10 points. Right? So if we add 10 points to this, all of a sudden we have an 89.2, and you still got your A. I mean, realistically, I would probably. So I don't think you need to worry too much. It's the power of averaging, right? Students stress out about high stakes events like midterms, where they come in and they want to have extra credit. And the real truth to doing well is to consistently get that regular credit. Okay. Any other? Oh, there was a question about the format. The midterm, of course, will have a multiple choice section, and it will have a free response section. And one of those will be calculator active, and one will not. And I'm not telling you which just yet.
So 2 free response to like 30, 40 multiple choices.
Something like that. Good. Anything else?
Is this like scaled, like the AP scale? Like
Oh, I like that.
You get like the multiple choice of the calculator or the first one.
Are you choosing your own, or are you just going to decide?
I have not yet formulated all the questions. I have. You like the calculator better? And students do tend to like calculator questions, which is funny because at the beginning of the year they're horrible at it. And the reason they're horrible at it is, and my Calc 1 students struggle with this. On the last quiz, I gave them an awful velocity. It was something like v of t is equal to cosine of t, cosine of the square root of t
Oh,
times t plus 1 or something like that. And I asked them to find all the times for which the particle is stopped. And I had countless students trying to solve velocity equals 0 by hand. And it's just a thing. You tell them, and I have told them that when you have the calculator in your hand, you should solve all equations with the calculator. You should. And for whatever reason, they see the word solve and they think must do algebra. And until you learn to let go of that, using the calculator solve. And the same thing, I asked them what's the acceleration at a given time, and I had a large number of people taking the derivative of this thing.
It really is a real problem. It's a calculator section. It says use calculator, but initially you're like, okay, I just want to solve it.
Yeah. Yeah, and it's because really of like 3 years of training in previous classes where it was all analytic methods. So, you know, I'm trying to get the calculator used to filter down to the lower sections.
But then like you also have like overkill where like some kids are like they just like get told to do with the calculator and
Yeah.
they never actually know how to do that.
Yeah, but interestingly, I don't get a lot of those kids at the level, well, do I? I do have some kids that, occasionally, some kids that do not know their multiplication class. So that's true. But anyway, all of that is to say, that's about the midterm. Good morning, Lydia. Good to see you. Today we're going to do a kind of niche topic, which is slope fields. Our story so far with differential equations has been there we go. Suppose I have a differential equation with initial condition like so. What are my solution options so far?
You mean solving that one?
Yeah.
Find equal y0 plus integral x0 to the x
Uh-huh.
xx
Let's call it t.
I dt.
Yep. You can call it any variable that x. This is the Riemann sum or definite integral option. And actually, this is really the way it's done numerically, computationally, in the wild. Let's actually call it the definite integral option, and there's a reason for that. Excuse me. And that is that as you get out into analysis, it turns out that there are other ways to think about integrating other than Riemann sums. So the definite integral stays, but the Riemann sum might not. Okay? What is my other major option other than definite integral?
Just looking the linear x no wait.
First, so I give you dy dx equals x squared, and y of 1 equals 2.
So y equals fx and parentheses x minus 0. No, sorry.
you're trying to do some linear estimation. Yeah, hold on to that thought, because we're gonna come back to that with Euler's method. But, I mean, you're overlooking the obvious. If I actually threw this problem at you, what would you do with it? You can practically do this. Yes, and how do I do that? Yes, exactly. So the other option is y equals the integral of f of x dx, which we call the antiderivative option. There are pluses and minuses to each. What are the advantages of the antiderivative option? Easy. Easy, familiar to you, okay? What else? Yeah.
You know what it is for any of them, you just have to do this.
Yes, exactly. Let's go ahead.
A general result.
It gets a general result. Take those two, put them together. We call that, it gives you a closed form. If you can get an antiderivative. And that general result of closed form is not to be sneezed at, no pun intended. It really matters that we can get a function we can look at and recognize, if possible, in, so that we can categorize it according to family. So that we can understand the internal logic of it. There's a whole lot of virtue of having a closed form solution, but what's the disadvantage?
C.
The antiderivative. Well, yeah, we got to do a little logical C, but we're great. That's
Not everything makes sense.
right, exactly. It can be hard to find an antiderivative. And if you go old school, and you look back in differential equation books, even going back to the maybe 1970s, you'll find that the differential equation books are full of, well, in this case, you got to do this to make the antiderivative work out for you. And in that case, you got to do that to make the antiderivative work out for you. And in this other case, and so what you end up with in the old school way of thinking about differential equations is a very large set of different possible cases, families of differential equations, linear, linear homogeneous, linear non-homogeneous, ones that can be done with variation of parameters, ones that can be so on and so forth. And all of that is fun. I really enjoy doing it, but it is also, to some extent, well, it just lacks generality. It makes differential equations a fairly technical and kind of hard exercise. So all of the advantages and disadvantages get flipped up here. This guy is less familiar, although with just a little practice we could solve that, right? Just use it more. But it gives us it's easy to find, relatively speaking, but it is not in closed form, and it is not general. So I end up having to solve each time I want a solution at a particular point. I have to redo another definite angle. And we saw that on the calculator that was fairly slow for the differential equation we solved. So what we would like to do is we would like to try to capture sort of the generality of the antiderivative, but combine that with something that is relatively easy to do and can be generalized to all possible differential equations. And so we're actually going to zoom out a little bit and expand the scope of our differential equations. And we're going to consider differential equation in the form dy dx is equal to some function of x and y. In other words, an implicitly defined differential equation with y of 0 equals x and y. So that's going to be our focus as we move out a little bit. As we do that, I want to consider, first of all, a graphical method called slope fields. You guys remember this from last year?
Yeah.
And the idea behind the slope field is that I'm going to be confronted with a differential equation, and I'm going to try to get a sense of what the different solutions look like. In other words, I'm going to try to find get a sense of the shape of the family of solutions. And to do that, I'm going to pick selected grid points. And at these selected grid points, let's say they are here, 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 this. Then for each selected grid point, I'm now going to compute dy dx. At each point. Now already that's a little bit of a warning flag to us because this tells us that this is going to be computationally intensive, which means that if I want a really good solution, I probably want to do this by computer and not by hand. Our slope fields done by hand are going to be crude. And then having computed dy dx at each selected grid point, I'm now going to sketch a small tangent segment at each point. Now what do I mean by tangent segment? What I mean is, I'm going to go through and I'm going to compute dy dx, and each one's going to give me a number. And let's say that at this point, let's say it's 1 comma 1, then my dy dx is equal to -2. That means that in the local neighborhood of 1 comma 1, my curve looks like a line with a slope of -2. So I can draw this guy right here, a tangent segment, as a local linear approximation of what my curve looks like. For x is close to 1, y close to 1, in the neighborhood of 1 comma 1. And by neighborhood, I really mean a circle at this time. Then my solution curve is going to look like a line with a slope of -2. And then I come over and my line has a different slope. Let's say -1. Let's say it's 0 right here. Let's say it's 0 right here. Let's say it's +1 there and +2. Then as I go, now I'm getting a sense of what the whole family of curves looks like. Does that make sense to everybody? Okay. Let's actually put this into practice. I want to go straight to the problems. Pull up AP Central on your iPad, and I'll pull it up on my desktop. It's left over from physics. And what's that? Yep. AP Central. Go to the AP problems, and we're gonna go for the 2000 exam. Exam information, exam home pages. Let's clear that ink out of there. And go to BC Calc.
Remember the exact physics problems? Firing the board under a block.
Yeah, famous problem. We're going to go down to problem number 5. No. 6. There we go. Problem number 6. And in problem number 6, we are given a differential equation. Notice that our differential equation is a function of both x and y in this case. It could be just a function of x. I mean, there's no restriction on this.
Is it for
No.
Oh, okay.
Okay. And so now what we're going to do is to draw a slope field for the selected grid points that they have right there. These grid points happen to be lattice points, that is, that they are points with integer coordinates. What you got?
Maybe the back to 2002.
It actually is.
It doesn't go like
Does.
I'm just trying to
So you have trouble finding it on yours looks different first. Interestingly.
it goes back to 2002.
Here at the top here. It should right there.
I'll show you.
That'll take you back around. Okay. Yep. Okay, you got it. You're working. You got it. He's got it. How about you, John? That'll get you there. I'm not sure what page you're on, but radio is on the fourth foot. You got it. Okay. All right. Now, we can actually take the method that I just described here, but I think there are some ways that we could be smart computers about it. Can you think of anything that might be kind of smart to do? Make our computational lives easy.
depending on the problem,
Yeah, that's right. Good. Do you see any opportunities for symmetry given the equation right here? Do you see any opportunities to use the idea of symmetry? It's like an even function, but it's not exactly an even function in that we have y minus 1 squared rather than y squared. But what does that tell you that there's going to be some symmetry about?
I mean, that's
Not x equals 1, but around y equals 1. That's right. We're going to have symmetry around y equals 1. You see it? Unfortunately, sadly, we don't have anything on the other side. That's right. So that doesn't really help us. But that did notice, we did notice something. Well, let's pursue that idea just a little bit further, because not only symmetry, but also what else would be particularly special right at y equals 1? Ah, yes! We have dy dx is equal to 0 at y equals 1. Yes? So one of the very special features that we're always going to look for vertical or horizontal tangents as special features before you begin. And if you think about it, isn't that really what we've been doing for a long, long time? Trying to set up a framework by looking for horizontal and vertical tangents. So immediately I can go through and go, hey, look at that, slope field, ta-da. Where else am I going to have slopes of 0? Like x equals 0. So now my problem is a much smaller problem. I really need to just compute slopes at 4 points. Go ahead and do that. Compute the slopes that we have there. I get a slope of 1 here, a slope of 2 there. and I get a slope of -1 here, and a slope of -2 there. Notice that they're not going to be very picky about, is this slope exactly -1 or is it -9? They're going to care about that. But they are going to care that this is obviously negative slope, and that the -2 is steeper than the -1. And so there we go. Now, how would you draw, how does this help us get a solution curve? Again, this is a pretty crude slope field, but if I needed to draw a solution curve with this, then I would draw a curve such that at each point I have a tangent line like on the curve. So for example, if I were to draw a solution curve through the point -1, comma 0, then I would draw it so that my curve is tangent right there, like that. And then it's pretty clear that it's got to be like so. And then it's pretty clear that it's got to be like so. What happens as I get close to here? Well, as I get close to here, you can see that the slope is getting close to 0. See how the graph tells me that? This whole thing acts kind of like a wall almost, because if I actually hit y equals 1, then dy dx will become 0, no matter where I hit. And as a result, it is not possible for me to go past the curve y equals the line y equals 1. Which means that my curve has to have a horizontal asymptote, y equals 1. And that means that my solution curve is now this and this. So I can draw solution curves through a given point just by following my slope field. And the finer grained my slope field, the better my solution curve will be, which is why computers are particularly good for doing this. No, was I supposed to get 4? Yes, I was supposed to get 4. Thank you. So my slope here should be 4. And again, the good people at AT will be able to tell the difference. Okay, slope of 2 and slope of 4. Thank you. Now, let's see here. Use the slope field for the given differential equation to explain why a solution could not have the graph shown below. This is not a hard question. We just have to wrap the right explanation around it. Why is this an impossible solution graph? Okay. We need a good, concise explanation. Do we agree that she's on the right track here? Okay. So all solutions must have horizontal asymptote y equals 1. This one does not. Good. Could we simplify that? We wonder, do all solutions have horizontal? We think that's probably true. Why can't this be a solution curve? Yeah, that's really the simplest way to say it. dy dx has to be 0 when y equals 1, and it's not. Yours will be fine, but I just wanted to simplify it. Caitlin and I were discussing proof or counterexample when we did school, just for this case, which is 6th grade. But I did explain the difference between proving that one even number plus another even number has to be an even number. You can't do that by just giving you one example. It was funny because I said, how would you prove that? She said, well, because there isn't any argument against it. And I said, that's not very good, is it? She said, no. So then I explained how you might generalize. You know, one even number is 2n, another even number is 2m. when you get to it equals 2, which is 2 times it equals 7, which isn't even up. Which is kind of cool with that. A little weird. So, but if you want to disprove something, all you need is a counterexample. So if I said all primes are odd, that's exactly what she said. She said 2. And I said, there it is, counterexample. And so what you did, Philip, here was you supplied a counterexample. Why is this the wrong solution curve? I don't need to go through all the details of where the person made a mistake here. All I need to do is to point out, your slope right here is wrong. Yeah. Good job. Also good job. Yeah. The rest of this involves separating and integrating, which you guys remember from last year. We're not going to do that at this time, but it's coming in the near future. All right, let's take a look at a second one. Clear the ink out of here. And let's take a look at the 2002 exam. So if you go to apsimple.collegeboard.com and go to exam information, I think you can pull up some kind of page that looks like this. And in 2002, the A. What I wanted to do here was just to illustrate what a more complete slope field might look like. And how you might use that slope field to answer questions such as A and C. B and D, well, we can do D also. The spirit of slope fields is to be able to solve a differential equation in the case where you can't do an antiderivative equation. And this is certainly one of those. If you remember that our basic method was, quote, separate and integrate, this is a non-separable differential equation. So the only method that we have for solving differential equations is not really helpful to us. If you were to go back a few years, it used to be that solving differential equations was a part of the BC curriculum, kind of did at the end of the year. And this would actually be called a linear non-homogeneous equation. You know the solution techniques for it. Okay, so they're given a slope field, and they ask us now to sketch the solution curve that passes through the point 0, 1, and then a solution curve that passes through the point 0, negative 1. Are you able to draw on the PDFs on your iPad? If you can do that, go ahead and do that at this time. Sketch the two slope fields. Except that this one doesn't just put it 0, 1. Yeah, you just also 0, negative 1. You have two wrong points. Okay, so I look at the point 0, 1, right? And I'm just going to follow the tangent segments. What do you notice about the curve through 0, 1? when I follow that tangent segment out, what happens? Okay, which way does the curve go? It goes like that, right?
Yeah.
And when I do, I hit another tangent segment, which just happens to be going in the same direction. So what does my curve end up looking like? I don't know.
No, it's going down.
Right? So this tangent segment here takes me to this point and this point, which are going in the same direction. John?
It's a illustration. It's all it's
Okay.
what was the question?
Yeah, I just want to know about the curve that goes through 0, 1.
Follows the lines of the other one.
So that in the end, what's shape do I end up with?
Relatively linear is what zeroes out at
It is relatively linear. Why does it zero out at the top?
the top. Because the slope line is 0 out.
No, they don't. Look at that. I trace this guy. Boom.
Oh, right through 0, 1.
Yeah, right through 0, 1. That one has this shape right here. What about the one through 0, negative 1? Well, this one's a little bit more curved. This guy goes here, he gets there, and he falls down off the cliff there. And then he goes, looks like he goes here maybe, and then it appears that he does something like that. Something like that. So we end up with those curves right there. Yes, it is very strange. Okay. I'm going to skip the Euler's method for another day. Back in part C, find the value of b for which y equals 2x plus b is a solution to the given differential equation. Justify your answer. What do you notice about this particular solution?
Linear.
It is linear. What do you suspect the answer to the question is?
Minus
0, 1 is the point in question, so answer the question, what's the value of b? 1. We suspect that c equals 1 is the answer. And now the question is, how do we justify it? And here we have to be careful, because the slope field is a graph, and that graph is not exact or precise. So if I were to justify it by saying, because when I draw the slope field, through 0, 1, it looks like a straight line, no credit for that. Because you're not sure if that really is a straight line or something that's close to a straight line. See what I'm saying? So we need to justify it, and the way in which we are going to justify it is really to show that this guy right here, here's the key word, is a solution. It's all about verifying that this is a solution. And hey, we've been verifying solutions for a while, right? We verify that this is a solution by substituting it into here and verifying that it solves the differential equation. So let me do that. Since I want y equals 2x plus b to be a solution, I go back up to here and I say dy dx is equal to 2x plus b minus 4x, and that gives me 4x plus 2b minus 4x, and that is equal to 2 times b. So this guy right here will definitely give me a solution. It will give me a solution when dy dx is equal to 2 times b. But also, dy dx has to be the slope of that guy. And so dy dx is also equal to 2. Well, I'm no dummy. I can see that dy dx is 2b, if dy dx is also equal to 2, then 2b is equal to 2, and b is 1. And we're done. So it's not just that our b is close to 1, which we got from the graph, it's that our b really is 1. And we got that by verifying that dy dx here and dy dx here were the same values. Notice that there was some intellectual come through going on. What we were doing was, on the one hand, verifying the solution by plugging in, and that got us a partial result. We got to this point. Then we came back and we said, it all has to be consistent. dy dx must also be equal to 2 right here. You see it? Another way to do this would be to reverse engineer it and to say, if I assume that y equals 2x plus b, plus 1, excuse me, then dy dx is equal to 2 from the slope, and dy dx is also equal to 2 times 2x plus 1 minus 2x, which is equal to 2, and that checks out. Why does this work? Why am I allowed to assume that this works out? Well, this logic only works if I'm guaranteed that there is a unique solution. If there are two possible solutions, this logic is not really valid. As it turns out, large classes of differential equations have unique solutions, and linear equations are one of those. We have just enough time, I hope, to talk about D. Let G be the solution that satisfies the given differential equation with initial conditions u of 0 equals 0. Does the graph of G have a local extremum at the point 0, 0? If so, is the point a local min or max? Justify your answer. Now, very, very interesting question. This question is going to rely on our using our wits and the stuff we know about local extremum. Tell me something you know about local extremum. They only occur critical points. Hey, is this a critical point? How would I find out? Aha! Yes, exactly. So by knowing Fermat's theorem, I can verify immediately that dy dx is equal to 0. Yes, we have a critical point. But does that make it a local min or a max? Not necessarily. How do I tell? Ooh, either first d-test, does dy dx change signs? Or second d-test, is the second derivative positive or negative? Min or max. Okay? Which one is going to be easier to use here? Turns out the first d-test is really hard to use, because since I'm in the plane right here at 0, 0, I would have to check for sign change kind of all around. See what I'm saying? That's, well, if I move x a little bit to the left or to the right, what happens to y? I don't know. You see the problem? So I consider, what if I do the second d-test instead? Well, that means I need to find d squared y dx squared, and that is equal to 2 times dy dx minus 4. And I know that dy dx is 0 right at that point. Boom, second d-test for the win. Isn't that nice? The first d-test would have been no help to me because I don't know how y changes when x changes. 0